Module 2, Lecture A, NumPy and Pandas. By the end of this lecture, you will be able to create NumPy arrays for numerical engineering measurements and grid-like data. Use Pandas DataFrames to load, inspect, filter, and summarize tabular civil engineering data. And convert between simple Python containers, NumPy arrays, and Pandas DataFrames when appropriate. NumPy arrays. Array creation. Creating arrays in NumPy is a key first step for working efficiently with numerical data. Arrays group repeated observations, such as sensor readings or traffic counts, into one organized object. Because NumPy arrays are built for numbers, they support fast calculations and consistent analysis across large datasets. NumPy helps organize engineering data in structures that match how measurements are collected. A single sequence, such as settlement or strength readings, can be stored as a one-dimensional array, while data from multiple sensors over time can be stored as a two-dimensional table of rows and columns. This makes NumPy useful for handling measurements organized by location, time, or other conditions. NumPy can generate arrays as well as create them from existing data. Engineers use arrays of zeros, ones, or evenly spaced values to set up models, simulations, and analysis tasks. These generated arrays provide an organized starting point for calculations, reduce manual entry, and help prevent errors. Python code. Array creation. Create arrays to represent engineering measurements, using small examples to keep the ideas clear. Before doing further calculations, check each array's shape so the data is organized correctly. We begin by importing NumPy, a library used for efficient array handling and numerical calculations. Since it is already available in Colab, no extra setup is needed. This lets us use NumPy tools for the engineering measurements and calculations that follow. A one-dimensional NumPy array is created to store settlement measurements in millimeters. Keeping these readings in an array makes them ready for efficient numerical analysis later. A two-dimensional NumPy array is used to store girder deflection measurements in inches. Each inner list becomes a row of data, creating a structured format with 2 rows and 3 measurements per row. This makes the deflection data easier to manage and manipulate. NumPy's linspace function creates 6 evenly spaced station distances from 0 to 100. This provides consistent measurement points along a straight path. We create a two-dimensional grid for initial groundwater head values with 3 rows and 4 columns. Every cell is set to 25 using NumPy's full function, giving the model a uniform starting condition for later simulations or calculations. We first confirm that each dataset has the expected shape. The settlement readings are one-dimensional with 4 values. The deflection data has 2 rows and 3 columns, and the groundwater head grid is 3 by 4. These checks ensure the data is organized correctly and help catch structural errors before any calculations begin. This section checks the main arrays by printing key summaries and dimensions. It reviews the settlement values, confirms the shapes of the settlement, deflection, and head grids, and displays the evenly spaced station distances. It also reports the average groundwater head, giving a quick overall check of the grid data. This script shows how to create and check NumPy arrays for engineering measurement data. It builds arrays for settlement readings, girder deflections, station distances, and a constant groundwater head grid, then prints their shapes and key summaries. The main purpose is to confirm that the data structures have the expected dimensions before using them in more advanced calculations. Array attributes. NumPy array attributes help verify how numerical data is organized before it is used in calculations or models. They describe key details such as the array's dimensions, size, total number of values, and data type. In engineering, checking these attributes helps ensure that sequences or grids of measurements match the real physical layout they represent. A NumPy array's shape tells you how its data is organized, such as a line, table, or stack of grids. This matters because a value's position can define its meaning. For example, when rows represent monitoring stations and columns represent variables. Checking the shape helps confirm that data was imported or reshaped correctly and prevents mistakes like mixing up time steps with sensor locations. An array's data type determines how its values are stored, which affects precision, memory use, and computation speed. In engineering, choosing the right type matters for both counts and precise measurements, especially in large data sets like terrain models or flood maps. Understanding data types helps keep data efficient, accurate, and reliable for analysis. Python code. Array attributes. When working with engineering measurements, inspect an array's key attributes to understand the data. Its shape shows how the physical measurements are organized, while its data type determines precision and memory use. We import NumPy to work efficiently with numerical arrays and mathematical operations. This gives the script the tools needed to manage and analyze engineering data. We create a NumPy array to store 4 hourly rainfall depths in inches. This gives a simple, efficient structure for working with the measurements and analyzing short-term rainfall patterns. A 2-dimensional NumPy array is used to store bridge deflection measurements in millimeters. The data is arranged as a grid with 2 rows and 3 columns, where each value represents a measurement point on the bridge. This structure makes the deflection data easy to work with and analyze later. We set the expected deflection grid shape to 2 rows and 3 columns. This gives a clear standard for checking whether the actual data is organized correctly. We check whether the deflection grid has the expected layout of 2 rows and 3 columns. The shape comparison returns a true or false result, confirming whether the data structure is correct before any further analysis. To quickly understand the rainfall array, we check 3 key attributes: its number of dimensions, its shape, and its total size. These tell us how many axes the array has, how many values fit along each axis, and how many elements it contains overall. We inspect the deflection grid array by checking its key attributes: the number of dimensions, its shape, and its total size. Together, these values show how the data is organized and how many elements it contains. We check the rainfall array's data type to see what kind of values it stores, which affects processing and memory use. We also check its total memory size in bytes to understand the array's memory footprint, an important step when working with larger datasets. We check the deflection data type to understand how the values are stored and how precise they are. We also verify that the array shape matches the expected layout, confirming the engineering data is organized correctly for analysis. This summary explains the grid layout. The data covers 2 girders with 3 measurement points on each. This clarifies the physical arrangement so the data can be interpreted in the correct engineering context. This script uses NumPy to inspect engineering data stored in 2 arrays: hourly rainfall and bridge deflection. It verifies that the deflection data has the expected 2x3 layout for 2 girders and 3 measurement points. It then reports each array's dimensions, shape, size, data type, and memory use. confirming that the data is structured and stored as intended. Grid data. Grid data in engineering is often stored with NumPy arrays, where measurements are arranged by rows and columns across space or time. This structure is useful for data such as elevation, temperature, or settlement, because each value's meaning depends on its position in the grid. Two-dimensional arrays let engineers analyze measurements in a way that matches the physical layout of the problem. NumPy helps engineers work efficiently with grid data by applying the same operation across an entire dataset at once. This makes tasks like unit conversion or temperature adjustment faster, more consistent, and less error-prone than editing cells individually. It also makes it easy to extract specific regions for analysis, supporting both large-scale patterns and local details. Grid data is central to engineering work such as visualization, simulation, and modeling. NumPy arrays provide an efficient way to store and process these structured grids, but the data only becomes meaningful when you understand what the rows and columns represent. With that context, raw grid values can be connected to useful engineering insight. Python code, grid data. NumPy grids can organize engineering measurements by keeping each value tied to its row and column location. Even small arrays can make spatial patterns easier to see. The script begins by importing NumPy for numerical work with arrays and matrices, and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the environment for data manipulation and plotting. We create a small two-dimensional NumPy array to store settlement measurements in millimeters. The grid has 3 rows and 4 columns, with each value representing a measurement at a specific location. This structure makes the data easy to analyze and manipulate using NumPy array operations. The program sets the expected grid size to 3 rows and 4 columns, then checks that the settlement grid matches it. If the shape is different, an error is raised so the data is verified before any further calculations run. The code converts settlement measurements from millimeters to inches by dividing the grid values by 25.4. It then identifies the maximum settlement in millimeters, highlighting the most critical point for evaluating structural integrity. We focus on the second row of the settlement grid, which represents measurements along the foundation centerline. Taking the mean of these values gives the average settlement for that section, providing a concise summary that can help reveal notable patterns or deviations. Set the settlement design limit at 8 millimeters. Then compare the settlement grid against that limit to identify cells that exceed it. Counting those flagged cells gives the total number of locations above the design threshold. The code summarizes the settlement grid by reporting its dimensions, the maximum settlement in millimeters, and the average settlement along the centerline row. It also counts how many cells exceed a chosen threshold and reports the maximum settlement converted to inches. The printed values are rounded for clear, readable output. This plot creates a heat map of the foundation settlement grid using a yellow to red color scale to show settlement levels. A color bar gives the settlement values in millimeters, while the title and axis labels identify the grid and its row and column positions. The layout is adjusted so the elements fit cleanly, and the finished heat map is displayed for analysis. This script uses NumPy to analyze a 3x4 grid of settlement measurements in millimeters, and Matplotlib to visualize the results. It verifies the grid size, converts the values to inches, finds the maximum settlement, averages the second row, and counts how many cells exceed 8 millimeters. It then prints these key results and creates a yellow to red heat map to make higher settlement areas easy to spot. Pandas data frames. Loading data frames. Loading data into a Pandas data frame is an important first step in turning raw civil engineering records into usable information. A data frame organizes data into rows and columns with clear field names for items such as dates, locations, measurements, and notes. This structure helps analysts manage mixed project data systematically and prepare it for meaningful analysis. Civil engineering data often comes from CSV files, spreadsheets, or databases, and must be loaded into a Pandas data frame with the correct interpretation. This means identifying column names, dates, numbers, and missing values accurately. If dates are treated as text or numbers as strings, later analysis can produce incorrect results. After loading a data frame, inspect it before starting analysis to confirm the data was loaded correctly. Check that the number of records, column names, data types, and first rows match your expectations. Issues like duplicate identifiers or unexpected values can reveal loading problems. So this quick review helps support accurate analysis and decisions. Python code. Loading data frames. Load the civil engineering records into Pandas. Then first inspect the columns to understand the dataset before doing deeper analysis. Keep the output brief and beginner-friendly. We import Pandas to work with tabular data and use string I/O from the input-output module to treat text as a file. This makes it possible to read CSV data directly from a string instead of loading it from an external file. We store a small sample of traffic data as a CSV-style string for quick testing. Each record includes details such as the date, intersection, direction, hour, vehicle count, and delay time. This lets us simulate reading traffic data from a file without needing an actual CSV file. The CSV text is loaded into a Pandas data frame by treating the string as a file-like object. The date column is parsed as datetime values during loading, which makes later date-based operations easier. The code checks the data frame's size by reading its shape information, which gives the number of rows and columns. It then prints a short summary of these dimensions, so you can confirm the data loaded correctly and is ready for analysis. Use the DataFrame columns attribute to get the column headers. Then print them to check the data structure. This helps confirm that the expected columns were loaded correctly. We print a short message before previewing the data. Then use the DataFrame head method to show the first two rows. This provides a quick view of the initial records without displaying too much information. The output is formatted as a clean string with the index hidden, so the focus stays on the data itself. Filter the data to keep only records with at least 400 vehicles, creating a smaller set that represents heavy traffic. Then count and print how many rows meet this condition. The code groups traffic data by intersection, then calculates the average vehicle count for each location. It rounds the results to one decimal place for readability and converts the summary to text so it can be printed clearly. This script gives a quick Pandas overview of a small traffic dataset. It checks the dataset size, reviews the column names, and previews the first two records. It then counts heavy traffic records with at least 400 vehicles and summarizes the average vehicle count for each intersection, rounded to one decimal place. Filtering data frames. Filtering a Pandas data frame means selecting only the rows or columns needed for a specific engineering question. In civil engineering, this helps narrow large datasets by site, date, material, condition, or inspection status. The result is a focused subset that supports decisions such as maintenance priorities or safety assessments. Filtering a data frame means selecting rows by applying conditions to its columns, such as numbers, text, or dates. These conditions ask logical questions, like whether a value is above a limit or a date falls within a range. By combining conditions, you can extract only the records you need while keeping the data frame structure intact. When filtering engineering data, always account for data quality and context. Missing values, inconsistent labels, and outliers can cause valid records to be excluded or incomplete records to be included. Check the filtered results against the engineering purpose, so the final analysis is accurate and meaningful. Python code, filtering data frames. Filtering helps select only the rows that answer a specific engineering question. With small data frames, these conditions are easy to check, making it simpler to create focused subsets from civil engineering datasets. We begin by importing pandas, a key Python library for working with tabular data. It provides the data frame structure, which helps organize, filter, analyze, and calculate results from structured engineering datasets. We create a dictionary to represent a small pavement inspection table, with each key acting as a future data frame column. It includes section identifiers for inspection areas and the material used in each section, such as asphalt or concrete. This structure makes it easy to convert the data into a data frame for analysis. The data records pavement inspection years, roughness values, and rut depths for road sections. Together, these measures show how recently each section was inspected, how smooth the pavement is, and how much surface wear is present. They are used to evaluate pavement condition and guide maintenance decisions. A dictionary of data is converted into a pandas data frame, which organizes it into a table for easier analysis. This format supports common tasks like filtering and summarizing, making engineering datasets more efficient to work with. We define separate conditions to filter the data for asphalt sections, records from 2024, and locations where the International Roughness Index, or IRI, is greater than 100. This isolates recent asphalt segments that may need maintenance, while keeping the filtering logic clear before the conditions are combined. The code filters the data frame using 3 conditions at once. The material must be asphalt, the year must be 2024, and the International Roughness Index must be greater than 100. The result is a smaller data frame containing only rows that match all of these criteria. We narrow the data to the key columns needed for review: section, International Roughness Index per mile, and rut depth in inches. By creating a new data frame view with only these fields, the analysis stays focused on the most relevant pavement condition measures. We first count how many rows remain after filtering the data frame, which tells us how many sections meet the criteria. Then we find the average International Roughness Index for those sections, giving a summary measure of their overall pavement condition. The output first compares the row count of the original data frame with the filtered data frame to show how much data met the criteria. It then reports the average IRI in inches per mile for the filtered rows, rounded to 1 decimal place. Finally, it displays the filtered results with only the selected columns and no row indices for easier reading. This script uses pandas to find pavement sections that may need review. It filters inspection data to keep only asphalt sections from 2024 with an international roughness index above 100. Then reports key fields such as section, roughness, and rut depth. It also compares the original and filtered row counts, calculates the average roughness for the flagged sections, and prints a concise summary for further analysis. Summarizing data frames. Summarizing data frames means turning large tables into key insights instead of reviewing every row. In civil engineering, summaries can show record counts, missing values, and average measurements from tests, traffic data, or sensors. These quick overviews help engineers understand patterns, check data quality, and decide whether the dataset is ready for deeper analysis. To summarize a data frame, first identify whether each column is numerical, categorical, or date-based. For numerical columns, use counts, averages, and ranges to understand typical values and possible outliers. For categorical columns, count how often each category appears, and for date or time columns, check the overall time span, observation frequency, and any gaps that could affect analysis. Grouping data in a data frame helps turn raw measurements into useful comparisons. Instead of summarizing everything at once, engineers can compare results by categories such as mix design, curing condition, location, time, depth, bridge type, or age. These group summaries reveal patterns like congestion, soil variation, or asset deterioration, making the findings easier to communicate and use in data-driven decisions. Python code. Summarizing data frames. Summaries help turn tables into useful engineering insight. Small data frames are especially helpful for learning, and group summaries make it easier to compare data in practical ways. We begin by importing pandas, a key Python library for working with tabular data. It provides the data frame structure, which helps organize and process data much like a spreadsheet or database table. This prepares us to create and analyze a concrete testing dataset. A small test dataset is created for concrete mix samples, with each record storing the mix type, test age, strength, and slump. It includes 2 mix A samples, one tested at 7 days with lower strength, and one tested at 28 days with higher strength. These records are intended for later analysis in a data frame. 3 records are added for concrete mix B. They show results at 7 and 28 days, including strength and slump measurements, with one 28-day strength value missing. This data supports tracking mix B's performance over time and highlights a missing value that may need attention. A list of dictionary records is converted into a pandas data frame, turning the test data into a table. This makes the data easier to analyze and manipulate with pandas tools. Start by checking the data frame's size to see how many rows and columns it contains. Then review the column names to understand the available attributes. Together, these checks confirm the dataset's basic structure before further analysis. Use the pandas describe method to summarize the numeric columns in a data frame. Then, round the results to 2 decimal places for readability. After announcing the numeric summary, display only the key statistics: count, mean, minimum, and maximum. This gives a concise overview of the main characteristics of the data. To find missing data in a data frame, use the isNA method to mark missing values as true or false. Then use the sum method to count the true values in each column, giving the number of missing entries per column. Converting the result to a dictionary makes it easy to read and print. The data is grouped by concrete mix, so the strength values can be summarized separately for each mix. For each group, the count, average strength, and maximum strength are calculated. Then the results are rounded to 2 decimal places. This gives a clear, compact comparison of strength across the different mixes. Filter the data to keep only tests with strength of at least 40 megapascals, then count the remaining records. This shows how many results meet or exceed the 40 megapascal design threshold. This script uses pandas to explore a small concrete test dataset with mix type, age, strength, and slump values. It reports the dataset size, column names, basic statistics, and missing value counts. It also compares strength by mix type using counts, averages, and maximums, then identifies how many records reach at least 40 megapascals. Overall, it demonstrates common pandas tasks for summarizing and filtering engineering test data. Data conversion. List conversions. Python lists are useful for gradually collecting engineering data because they are simple to create and extend. When it is time to process numbers or compare many observations, converting the data to a NumPy array or pandas object makes analysis more efficient. This keeps the values organized in a form better suited for numerical computation or tabular work. Converting a list to a NumPy array makes numerical analysis faster and more consistent across a dataset. It is useful for measurement data because operations like averages or unit conversions can be applied efficiently. Equal-length nested lists can also become matrix-like arrays for working with rows and columns. This works best when the data has consistent types. Choose between NumPy and pandas based on the kind of data and analysis you need. NumPy works best for uniform numerical data and calculations, while pandas is better for mixed data types, labeled columns, filtering, grouping, and table-like records. Making the right choice helps keep engineering data organized and analysis clear. Python code. List conversions. Civil measurements often begin as simple lists, but they become more useful when organized into analysis structures. Arrays and tables help arrange the data so it can be examined and interpreted more effectively. We begin by importing NumPy and pandas, 2 key libraries for working with data. NumPy supports efficient array handling and numerical operations, while pandas is used for analyzing and manipulating tabular data. Together, they prepare the script to convert lists into richer data structures for later analysis. A set of engineering strength values measured in pounds per square inch is first stored as a list. It is then converted into a NumPy array of floating point numbers, making it ready for efficient numerical analysis. Convert the strength values from pounds per square inch to megapascals by multiplying each value by the appropriate conversion factor. Then use NumPy's mean function to find the average converted strength, giving a concise summary of the data in megapascals. Create specimen identifiers from C1 through C4, then use them with the corresponding concrete strengths in PSI to build a pandas data frame. The data frame stores the identifiers and strength values in labeled columns, giving the data a clear table structure for later analysis and manipulation. A new strength column is added to the data, using megapascal values rounded to 2 decimal places. Then the data is filtered to create a smaller set containing only specimens with strength of at least 4,000 psi, identifying those that meet the required threshold. A nested list of elevation values is converted into a NumPy array using floating point numbers. This makes the elevation data easier to analyze and supports efficient numerical operations. Define the expected elevation data as a 2x2 grid. Then use an assertion to confirm the actual array has that shape. If it does not, an error signals a problem with the data structure. This check helps ensure the grid is organized correctly before further analysis. The output first shows the original strength values in PSI, then reports the average strength converted to megapascals and rounded for readability. It previews the specimen data with IDs, PSI values, and converted megapascals, and counts how many specimens pass the minimum strength requirement of 4,000 psi. Finally, it verifies the elevation grid by printing its array shape to confirm the expected dimensions. This script shows how to turn simple lists into structured data for analysis with NumPy and pandas. Concrete strength values are converted to an array, changed from psi to megapascals, and averaged, then organized in a data frame with specimen IDs and filtered to find values above 4,000 psi. It also converts a nested elevation list into an array and checks the grid shape. Overall, the example demonstrates how lists can be transformed into more useful formats for calculation, filtering, and validation. Data frame conversion. Data frame conversion means moving data into or out of a pandas data frame so it is easier to inspect, clean, analyze, or share. Data frames are useful for engineering data because they organize values with labels, such as columns and rows. Converting simple collections into a data frame gives the data a clear structure, making it easier to filter, summarize, and compare measurements. In engineering analysis, converting data into a data frame helps organize changing datasets into a clear, labeled structure. Data from spreadsheets, arrays, or simulations can be aligned by variables such as sensor location and observation date, making it easier to interpret. This labeled table format also improves communication because it is clearer than raw numbers for engineers and project managers. Converting a data frame to another structure helps match the data format to the task. NumPy arrays are often better for numerical modeling, optimization, or machine learning when labels are not needed. Lists and dictionaries can be useful for small datasets or simple summaries. The main goal is to choose the structure that keeps the workflow accurate, efficient, and flexible. Python code, data frame conversion. Choose the right data container based on what matters most. Use arrays when numerical computation is the priority, and use data frames when labeled rows or columns are important. We start by importing key libraries for working with data. NumPy supports fast numerical operations, while pandas helps organize and analyze structured labeled data. Together, they prepare raw data for easier manipulation and insight. Basic field measurements are stored in separate lists for road segments. One list holds segment identifiers, another holds each segment's length in feet, and a third holds condition scores that describe segment quality. These lists can then be combined into a structured table for easier data analysis. We create a pandas data frame from 3 lists containing segment IDs, lengths in feet, and condition scores. These become labeled columns, making the data easier to organize, manipulate, and analyze than separate raw lists. We preview the data frame by printing a short message and showing its first 3 rows. The head method gives a quick sample of the data, and converting it to a string without row indices keeps the output clean. This lets us check the data frame's structure and contents without displaying too much information. Select the numeric columns for length in feet and condition score, then convert them from the data frame into a NumPy array for efficient numerical work. Finally, check that the array has 3 rows and 2 columns, matching the 3 segments and 2 numeric attributes. so the data is in the expected form before further calculations. Convert the road segment lengths from feet to meters by multiplying the length values by 0.3048. Then, calculate the average of the converted values to summarize the typical segment length in meters. A new data frame column is added to store segment lengths in meters, with each value rounded to 2 decimal places. The mean segment length is then calculated and printed, also rounded to 2 decimals, giving a clear summary of the average length in meters. Convert selected data frame columns into a list of record dictionaries, where each dictionary holds one row using column names as keys. This record-based format is useful for reports because it is easy to loop through and read. Printing the records then gives a clear view of the data's structure and contents. The code prints a short key idea explaining why different data structures are used. Lists organize the input data, arrays support numerical calculations, and data frames label and display the results clearly. This reinforces the purpose of choosing each structure for its role in the workflow. This script shows how to organize road segment data using lists, arrays, and a pandas data frame. Lists provide the input data. A NumPy array supports calculations such as converting lengths from feet to meters and finding the average length. And the data frame labels and stores the results. It also rounds the computed values and converts selected data into a dictionary for reporting. Container conversion. Container conversion means moving data between basic Python structures and tools like NumPy and pandas. In engineering workflows, data may start as lists or dictionaries, but NumPy arrays are better for numerical calculations, while pandas data frames are better for labeled organization and summaries. In general, use lists to collect data, arrays to compute with it, and data frames to organize it clearly. In civil and environmental engineering, raw data may begin as lists or dictionaries, but the best structure depends on how it will be analyzed. NumPy arrays work well for numerical calculations because they treat data as one numerical object. Pandas data frames are better for data with related fields because they preserve column relationships and make tables easier to interpret. When converting data between containers, preserve the meaning, not just the format. Adding labels or units to a data frame can make values clearer, while converting to a NumPy array may remove important context. Basic Python containers can help with reports or exports, but always make sure the data still accurately represents the engineering information. Python code. Container conversion. Choose the right container for engineering data based on the task. Use arrays for numerical calculations, and use data frames when working with labeled tables. We start by importing 2 key libraries for data work. NumPy supports efficient numerical operations with arrays, while pandas helps organize and analyze structured data using data frames. Together, they provide the foundation for converting and manipulating engineering data in different container formats. A list of strength values in pounds per square inch is created, then converted into a NumPy array using floating point numbers. This makes the data ready for efficient numerical calculations with NumPy. Convert the strength values from PSI to megapascals by multiplying them by the standard conversion factor. Then, use NumPy's mean method to find the average of the converted values, giving a single representative strength in megapascals. The data is organized in a dictionary that groups each cylinder with its strength values. It includes cylinder labels, the original strengths in PSI, and the converted strengths in megapascals. The converted values are rounded to 2 decimal places for clearer presentation. This structure makes it easy to turn the data into a data frame for further analysis. The data is first converted into a pandas data frame so it can be handled in a structured table. Then the table is filtered to keep only cylinders with strength values of at least 4,000 psi, creating a smaller dataset focused on higher strength results. The filtered data frame can be converted into simpler data structures for further work. The cylinder column is turned into a Python list of labels for the strong cylinders, while the strength in megapascals column is converted into a NumPy array for efficient numerical analysis. This section checks how concrete strength data changes as it moves from a Python list to a NumPy array and then into a data frame. It confirms the data structure and array dimensions, calculates the average strength in megapascals, and verifies the data frame columns. It then filters for cylinders stronger than 4,000 psi and converts their megapascals values back into a rounded NumPy array for clear display. This script shows how Python data can move between common container types. It begins with strength values in a list, converts them to a NumPy array, changes the units from psi to megapascals, and computes the average strength. The data is then organized in a dictionary and a pandas data frame where cylinders with strengths of at least 4,000 psi are selected. The output reports the key container types, the average strength, the data frame columns, and the selected cylinder labels and strengths. In this lecture, you learn to create NumPy arrays for numerical engineering measurements and grid-like data, use pandas data frames to load, inspect, filter, and summarize tabular civil engineering data, and convert between simple Python containers, NumPy arrays, and pandas data frames when appropriate. In the next lecture, Lecture B, we will go over cleaning and visualization.
Thank you for your attention. See you all in the next lecture.